¿Qué tal? Muy buenas tardes.
Hello, good afternoon, rather evening to all of you in this room, the ones following us on streaming. This is the very last workshop for the second session in our CyberCamp 2018. For those of you joining us now, whether in the flesh or via streaming, let me remind you that you can go to social media, you can go to Twitter, at CyberCampS and the hashtag CyberCamp18. First of all, let me apologize because of the technical problems with the background display. We have this one as a replacement, a temporary displacement, but we also have Jacob Fernandez Hansen, CEO at Whitefence, with us, and he will be teaching this technical workshop or building an undetectable Wi-Fi shell. He's an ethical hacker. He's an expert in network infrastructure of all sizes and has a long and extended professional experience. An applause for Iago. Thank you very much. Hello. Thank you. Thank you for being here attending this seminar. I hope I don't bore you. If you look up, careful, and you don't get a present from up the skies. Maybe there is a gap in between the curtains. I'll try to conduct this workshop so this would be an average level. I know there's people coming from the university, from the high school, from everywhere. I'll try to keep an average or a mid-level. We'll have time for a lot because it's 2 hours, but I'll try and make sure that this is an introduction to Wi-Fi programming. Basically, we want to make sure that people understand that not all tools are just made. We can customize and produce our own tools. I've been working on Wi-Fi for many years now, and relatively just a few years with my own tools. So that's what I want to convey, this option of having our own tools. Those of us working with the Wi-Fi networks, at a given time, we might know that we might not have the necessary tools for whatever they represent. We need to program something fast. And this is our idea. Maybe then, what about a shell? If maybe, ideally, it should be hosted on a Wi-Fi or a Wi-Fi packages. Well, that's not it. What matters is learning how to do things that are out of the box, so to say. We have the logical analytical skills. We don't see things as others do. We try to break down things, we try to change them into fragments in order to understand them. And that's the idea here with this conference.
Then the code you can find on GitHub. So, what can we do? How can we program on Wi-Fi packages? That's the point. Here we see the table of contents for the presentation. Python as a programming language, if it's for gamers or not, that kind of controversy or debate. Then I will tell you about my library, Scapy, for patching. And that's not exclusive for this. It's for patching networks in general. You can do all sorts of things on Scapy. And then we will see what we need on pen testing, what kind of toolkit we need, what tools are best, what kind of cards are available on the market. We will see some steps for programming. I will explain a little bit about code we can write, and I will simplify matters as much as possible to make this accessible as foundations or introduction. The repository on GitHub, well, I'm happy to let you have all of that. And then there's Monitor SH, which is the way I initialize monitoring cards at the moment. This is like a script. I strongly recommend it because any Wi-Fi card that's connected to a laptop, for instance. I'm going to be talking about Linux, by the way. If I mention Windows rather than Linux, it will be to just get rid of it or destroy it. And then I will tell you a little bit about one of the programming exercises to run cards on monitor mode. I will then analyze code. I will explain why I did it that way, different fragments, different functionalities of that code, so you can then read code on Python and understand what you're reading. And then what I really like, I'll be exploring some concepts. I didn't bring videos. I like being courageous and I like risk. So sometimes things work out, sometimes they don't. So let's keep our fingers crossed. Let's hope that it works today. I've done my best to bring it so that it will work. So there's a lot of bibliography. My name is Iago Hansen. That's my alias. You can find a lot of literature that will say how I've done as much as I could to disseminate everything that has to do with hacking for many years. So let's start then with Python. Poor old Python in the world of programming languages. People who program at a lower level tend to complain and say, oh, Python is just a language for lamers. It's useless, it's too simple. Well, I don't agree. More and more, it's becoming the hacking language for concept proofing, because we can import any library from the internet and do things that it would have taken us ages to do. We don't need to prepare our own library, nothing like that. Python provides us with that. And for people who are bone idle like me, it's a great tool. And it's ideal for proof of concept. In 10 minutes, you can get Python to make things work. Maybe not as well as you would dream of, but it works. And we have libraries on patching of networks like Scapy, or for scraping of websites, all sorts of libraries. It's amazing. You can just install a library and half a minute later you have your interesting library to do all sorts of things with. What's the main problem there? Well, that libraries are not documented enough. We do pip install, and who knows if that library has been constructed properly. It's a matter of just testing it and seeing if it works okay. Community has done a lot to make Python better. Which release is better? Well, I'm still on version number 2. I'm not doing 3 just yet. And again, there's so much documentation on Python, literature, tutorials, videos, all sorts for you to learn how to use Python. What are the drawbacks? That Python is not efficient, not particularly efficient. It has been improved over the years, but is not an efficient language. Is good for proof of concept, but not really for production. I'm not saying that nothing is produced on Python, because many of the tools that you will see, well, you will get your little box that might be worth thousands of euros. And what does that contain? Well, Linux, shell, and Python, and not a lot apart from that. And people are selling that, but it's not the ideal language for products because it lacks efficiency. It's an interpreted language. It's not a compiled language. If you know what I'm talking about, that's a big difference, right? As far as efficiency is concerned. It's a scripting language. It was designed for sequential programming. And, well, then it's got object-oriented properties that have been added over time. But it's a little bit more advanced than share scripting, but not that much more. What about multi-thread? Well, working with different threads and processes. Does multi-threading work well on Python? Not particularly well, because it's kind of emulated. Threads are not real versus a processor. It has waiting status, waiting for other threads to come in, and you need to work with threading. Logically, most of the programs in hacking work with threads because we need to work in parallel. You can't just do sequential language jumping from one point to the next. There are times where programming requires threads and threading. So threading is present, but it's not wonderful. And then another drawback, when people say that Python is multi-platform, well, I think that's not quite true. Python can be installed on Windows. You can do certain things like that. But Python was designed for Linux, not for Windows. So the way you work with drivers and binary code, it's all designed for Linux. And I think it's awful when I see it working with Windows. So now, what is Scapy? Well, it's a Python library. It's powerful. It's a wonderful Python library, very much advanced from the programming point of view. It's really active, very often updated. So we can basically say it's a library to handle and patch packages. Some functionalities like Wireshark that captures, manipulates, and patches network protocols. Scapy does that because it can understand all these different network protocols. I'm going to be focusing today on Wi-Fi, so because for me that's the main part of Scapy. But in fact, you can do all sorts of other things as well. Some very simple tasks, for instance, an attack or to spoofy or man in the middle. How can you do that? Well, small tools like Undetectable. Well, there are many different tools that you can use for man in the middle activities. And in Scapy, the library might give you what? 20, 30 programming lines, but they're very powerful for ARP, EAP, RDP. It can handle, as I said, many different protocols, so we can then work with them for programming purposes, which is very practical again. Otherwise, you would have to program your own tools, which is nice, right? You have an idea, you'd search Google, you might find bits and pieces of proof of concept on GitHub, and yet you end up deciding that you'll have to prepare your own and program your own tool. And that's what you can do with Scapy. And many of the tools that you'll find on open source for particular attacks have been designed on Python and Scapy. And if you import your Scapy library, you'll have all those tools and functionalities. Then it can do a number of different things as well. For instance, package manipulation possibilities. What does that mean? Well, that you need to first be able to capture the traffic. Great. Well, SCAPI allows for that. You can capture a card, or whether it's for the internet or the Wi-Fi. You can find information like that. Then you can also handle and manipulate and modify information and traffic, finding certain packages, changing some properties, and then do all sorts of things, including interpreting the package. True, but more than that. Instead of the package going from A to B, you can change A, the origin, or the destination, or the timing, or the sequence. You can change one or a number of things on that package, and because you can manipulate and handle all things, you can then inject it back again into the air, the Wi-Fi, or Ethernet, whether it's cable or Ethernet, whatever. So you can capture and manipulate and inject back again. Those are the basic functions. And then why do we talk about patching a package? Well, a package is quite complex because it's a binary object moving on a network traffic, whether it's Wi-Fi or whatever. So we find a network package or whatever. But a hexadecimal editor, in fact, sometimes has trouble showing us enough details on a package because we're not going to be working with bytes, but with bits. So the difference between 0 and 1 is like a flag. And if I try and view a package hexadecimally, I would only see at the byte level, and that's not good enough. I need to go down to the bit level, and it's not always as accurate as saying, oh, this will take 2, this will take 1, or the beginning or the end of the field is not that simple to track and understand. It's very complex. Fortunately, the SCAPI library shows me the fields in the package in a way I can understand. So that's dissecting or patching that's parsing. When we talk about ERP, ARP, Ethernet, IP, TCP, we can get to all different layers of any package. So apart from dissecting, so we saw 2 functions at the beginning of my presentation. Is capture, that's sniffing traffic. That's one of the possible functions. Another function is injecting traffic into the network. What other functions can we have? Show me differences between these 2 packages. That's another function. Show me a beef or show me a hexadecimal output, seeing the roar of a particular package, to see the size. It's got all these different functions so that we can better program the network functions. SCAPI is also available for version Python 2 or 3. I'm currently using Python 2, but Python 3 is also very, very much developed. What are the drawbacks? There's very little documentation. You will find many different things on the internet, but there's a little bit trial and error. Is not documentation as such. You might see programs that somebody else has done, some blogs, some articles, documentation on SCAPI, which is still a little bit poor. So it's not very solid from that point of view. Here, well, I'm going to do a little bit of publicity of my book that I have published recently. You can find it on Amazon, and I brought a few copies as well to offer you here today at a good discount. So that's SCAPI for Wi-Fi. That's what you will find if you get my book, with 40 different examples, with comments for different functionalities, and so that you can learn and move up in difficulty, for you to first understand how Wi-Fi works, the internal protocols there, and so that you can then start testing with Python and SCAPI. Now, let me tell you a little bit now about hardware. What hardware will you need if you want to work with Wi-Fi like this? Well, a card that can work with a monitor mode. And there are many like that in the market. My laptop, for instance, has an Intel card that can work on monitor mode. It's a pretty good card that allows me to do many different things, although it has one drawback I'll tell you later. There's another one here, Alpha. And in fact, if you have the money, I would recommend you to get it now, because in 3 months' time it will stop. It won't be sold anymore. And this is a fantastic chip. 9271, one of the best chips ever. Unfortunately, Atheros is not making that chip anymore. They have more modern versions, but this one is better, to be honest. The other one, the Intel L, the white one, which I'll be using for my demo. They both use the same Athero chipset. There are very few left in the market. The Alpha card is technically a little bit better than the TP-Link, so that's why I still recommend it. Now it's still available. Logically, it's a Kali Linux card, implemented for all different versions or releases. It can work with Python from 2.5, 2.7, 3 as well. It works really well with SCAPI libraries, so that's what I recommend. But you need to understand the difference between a monitor mode or promiscuous mode card and a card with injection capabilities. For those of us who've been working on Wi-Fi hacking, that's a very important difference, because not all cards on monitor mode allow for injection, or injection at the same level, or sniffing the same level of information, depending on how the driver, the module, was programmed for the card. Not all modules have been programmed properly, which is why I recommend Atheros. The hardware of that card is really good. It allows for monitor mode, as I said, and that means that I can sniff out any package, whether it belongs to my network or not, no matter where it comes from, where it's going. Because I'm on monitor mode, I'll be sniffing any package on any network, which is a little bit similar to what is called promiscuous mode. Monitor mode and promiscuous mode are almost synonyms, although not quite. Because when we say promiscuous mode, it means that the card within the segment, within its segment, it will be sniffing traffic. So if it's connected to the CyberCamp Wi-Fi network here, then it will be able to sniff out the traffic from any system connected to CyberCamp Wi-Fi. but not on monitor mode, because the card is not connected to any mode, really, and then it can sniff out any network, any system within a particular range, geographical range, not necessarily connected to a particular Wi-Fi network. When I work with Wi-Fi, I want monitor mode, not promiscuous mode. And also, what's the difference between some monitor modes and others, depending on what card we use? Because packages have different layers, as we will see shortly, and some monitor mode cards give me all layers, whereas other cards only give me the layer 811. Well, I don't want that one, only I want the previous layers as well. That's a good monitor mode card, and it even for packages that are corrupted or with a CRC error, a good monitor mode card will provide me with any package, even if it's wrong. And later we will see the different layers, kernel, the drive, whatever. Basically, what I want is ending up with all those layers at the user space in that area, so that I can analyze and see things that otherwise I wouldn't see. So those differences are important. Some monitor modes don't allow for injection. For instance, the Intel card in my laptop allows for it. Great. That means it gives me most information from all the different layers. But if I try to inject with that card, it won't let me inject packages because it's monitor mode without injection. Those are basic differences as far as hardware is concerned. And then cards can be better or worse from a physical point of view because of the manufacturing process, the type of chipset, the frequency elements being better or worse. Normally, the most expensive ones are better. This alpha card is then different from a TP-Link like the two that you can see up on the screen. They all have the same chipset. So you might say, oh, I'm just going to get the cheap one. Well, it's not just the chipset. There are many different components, electronic components and materials, and the RF measuring, many different qualities. So logically, some cards will be sniffing better than others, depending on that quality. So that's all I have to say about the hardware. And my recommendation is having one or two good cards that work on monitor mode. That's basic. Now, let's move from hardware to Wi-Fi. What is Wi-Fi? What is the brand? There's a brand name, Wi-Fi. That's the commercial name. That's it. But what do we mean when we say Wi-Fi? Well, it's a standards association. That's IEEE Cube. They are in charge of protocols that are called 802.11. Those protocols all refer to wireless communications in the standards that IE Cubed or IEEE publishes. So we say 802.11. What is that? It's not just one protocol. There are many protocols there. There is a whole array of protocols included. For instance, the legacy ones, the basic ones, the first ever version, and then 802.11, 802.11a, b, n, ac, w, pr, all sorts. Now, 2 letters are used, AC. They've run out of letters in the alphabet. Can you imagine how many protocols Wi-Fi includes then? Wi-Fi is just a brand name that says a piece of equipment that has Wi-Fi on it, is compatible with all those different protocols that are interoperable. So my product, Intel, for instance, is compatible with any other type of Wi-Fi. So, as I said, 802.11 includes many different protocols. 802.3 is the most popular one. That's the Ethernet cable, the cable that you physically connect to your computer. And Ethernet works so well that it was like the foundations for Wi-Fi to grow and be developed for the 802.11. It started with Ethernet, and then Wi-Fi made the most of that initial development. So this is still very active. Many different protocols continue to be launched because Wi-Fi continues to be improved. Later, I will tell you about some of those improvements. So, what is that 802.11 frame like? Well, this is it. This is a network frame. And what's the difference between a package and a frame? Even professionals get confused. Sometimes we ask for a clarification. Are you talking about a frame? Or what is it? Well, in a frame, we're talking about the most basic, the smallest possible unit. That would be a frame. Whereas a package is different because network frames are a little bit like onion layers. So if we're familiar with the typical standard, the basic one, the OSI layers, going from 1, 2, 3 different layers, with one is physical layer, another one for links, another one for network, whatever, and on up to layer number 8, and that would be us. So every layer encapsulates certain information within the package. So if I go to the lowest layer, that's layer number 1, what does that work with? Well, the physical part of our environment, saying what physical characteristics or features an Ethernet cable should comply with. 8 threads with 4 pairs, with certain electrical features, with a certain impedance, a number of physical characteristics. That's the first layer. If we talk about 802.11, what would the physical layer be regulating? Well, the frequency, the band, the modulation for radio frequency, timing for a package to be up in the air, or a transmitter transmitting. That would be it. That would be the first layer. So 802.11 regulates the first layer, the physical layer of the radio frequency transmission, and importantly, the second layer. What does that involve? Well, how communications have to be regulated on a Wi-Fi network, how a station has to transmit or then retransmit, how different systems can coexist in the same environment and avoid any collisions if transmissions happen at the same time, how traffic has to be regulated. All of that belongs to layer number 2. That's the MAC layer, traffic going from one device to another through the MAC. That's why we never talk there about IP or ports or VP. We just talk about MAC there. That's why people often refer to that second layer as the MAC layer or the linking layer. So the only addresses handled there are MAC addresses, that is physical addresses. Every device has one single MAC address in theory. Although if you buy a Chinese device, you will find there are a number of them with the same MAC address, and VP 14 because they're almost out. Well, now we have the 16, and the same thing is happening with Macs, which are growing larger and larger. A mobile device or a Wi-Fi card or another Ethernet device should have one single MAC address, because if there are two with the same MAC address, that allows for traffic collisions. So a frame moves on layer number 2. So when I talk about frame, remember that I'm talking about layer number 2.
But apart from regulating communications, and we will see a few cases on how this is regulated, that frame, in the end, what's the role there? It is all about transferring information, that's it. So I want to have access to a website, I need to see the result of my surfing, pictures, all the content, all the traffic. That's what has to be transported, right? That's communication. So that frame has layers, as we said when we started, those layers. If I had to transport data, I add layers, and in the end, it turns into something that is known as a network package. So we can dissect or parse the package and went into layers. I say this IP, this is TCP or UDP, and this is what's known as 802.11, but all up in the air is a summation of the whole package. That's the difference between package and frames. So this is the difference in the protocol. And a package has already a nexus, has a payload that has all the traffic that is moved around. So this is what an 802.11 framework looks like. We need to pay attention to it because every field there, such as the the first one that is the control layer that will give us information when programming, and that's what SCAPI. That's what SCAPI is dissecting from every package, network package. So if I say, this is what I have, which is a package or a frame moving around my network, and I capture it and send it to SCAPI, and I say, show me the address number 1 for this package. So that is a destination. So we check this out, and we say address 1. Where is it headed? Where is that going? From where to where? So source and destination. And here we have part of it, which is address 1, and this other part here is address 2. So we have two fields that are clearly source and destination, and with that I can already work around with those two fields. I can just say, okay, so I just want to capture traffic headed here to Jago's cell phone. Only the traffic where the destination or the source is this Jago's cell phone. And with that, I can start programming, and I can have my own tool. So same, I'm sniffing traffic, but on what conditions? Address 1 is Jago's MAC address. Address 2 can also be my MAC address. So that's a sniffer, which is a targeted sniffer. But then we see that there are 4 addresses in the package. So we see address 1, address 3, address 3, and 4. So different types of addresses, and this is because of the way how it's been done. This is a network where we have intermediaries. Who is the intermediary there? The hotspots, the access points. So basically, my cell phone maybe wants to talk to your phone, right? But then my cell phone will not be in communication with you. My mobile will talk to the hotspot, and that will transfer the package to you. That's the way to produce the Wi-Fi communications. How come there is no paired communications? Well, there is actually. There are peer-to-peer communications, which are IBSS. This is peer-to-peer There are different names for it, but they go unused. They don't work. It's never been used, and only a few people use it. Some HP printers and just like that. But any communication on Wi-Fi with infrastructure moves from a station through the access point and from there to another device that can be on the wireless network or the wired network, right? So what's an access point good for? So intermediary for communications, then it's also a media changer. So it changes packages going through the air and fits them into the wired network. That's the mission there. That part of an access point where you bring together an RF, which stands for radio frequency, and a wired network is known as a DS, or distribution system, and we will explain that. So when you hear distribution system, it is the wireless or wired part of a Wi-Fi. It is wired because it leads to a DS, or wireless because it moves from the DS to the wireless part. What else? So first line, and I will forget about our other headers, but we move from frame control to the FS. That is how you break down a package. You have a frame control, you have a duration, you have all 4 directions, you have an SC, which is a sequence counter, so that's the sequence it follows, and so the first one is 1, then 2, then 3, then 4. And why is that? To see if there's any package that's gone lost in between, and we need to resend it because it happens all the time. And then we have the green side, which is the body, or the frame body. That's where you transport information for the package. Okay, so that's what's transported by the package. That's the body of it. And then an FCS, and that, as usual, that's the check control, or the RCC, as it turns out. Again, a summation from the front to the back, and if it matches the value, it's reached its destination, right? And if it's not a match to the back summation, then the package is got here, but it's been broken in between, so we'll have to discard it and ask for a new one. I play around with it often because I have clips in Python, as we will do today, because I truly prefer the package. So when I want to do something hidden or masked that cannot be easily sniffed, such as today's proof of concept, I try to make that incorrect. So why do you want it to be incorrect? Well, because if it is so, a regular Wi-Fi board will rule it out and will not even show it. So the drivers layer for the board will say FCS incorrect, you don't send it to this user space. So that's a way to go in and unnoticed or hidden. There are other fields such as frame control, the first one, which in turn we can split into two fields, and that's the important one. This is a very small one. This is just a few bits we're talking about. First, frame control is just 2 bits, if I'm not mistaken. Version, they're all 0 now, so the version implementation is not being used. Type and subtype, okay, that's important. When I get the package up in there, so here I'm sniffing it, and first thing I need to know is what type is it and what subtype it is. There are different types of packages and subtype of packages as well. First, we can talk about type 0 that I'm very interested in. These are management packages, or frames, rather management frames. So these are the beacons, and they release access points constantly. I'm here, 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 and here, and these are my features. Or there as well, the de-authentication. So I de-authenticate from the network. That's a management frame, or I get authenticated on the network, or I get associated to the hotspot, to this area here again. So this is what I find is most interesting most of the time, depending on what I need to do, but most of the time. And then we have type 1 and type 2. Type 1 are frames of data, and type 2 are control. Type 1 are data frames transporting data to higher layers. So it can be Wi-Fi communication or Telegram or WhatsApp, whatever you choose. That's information. Those are packaged data. And then control. Control are those that say, I haven't got the package, send it back to me. This package it doesn't have AC key or RTS, CTS. So I'm not interested at all in this. And this is what will be used for, here we will only use 0, which is management, the most interesting ones. So what about subtype? As part of the management subtype, which is so what about deauthentication? Well, deauthentication is this. And what a beacon? This is this. This is number 8. And what about a prop request? Seeing whether my favorite network is available. This is type 4, just to name a few. And so with type and subtype, we defined what we are looking for. So these are very important, and this is the first thing that we see with SCAPI. Then DS, we said DS. DS is what's wired, as we said. When we get a package up in the air and they say it comes from their DS package to 1, what that's saying is that this is a package up in the air because it's sniffed it up in the air, undoubtedly, but the destination is the wired network. Can be the gateway, an internet access point. That's a package that has a DDS bit to 1. And when you go online, there is a request for the site, but then there is a response. If I get one up in the air from DS1, that means that comes from the wired network, the internet, for example, and leading to a device on the wireless part of it. So that shows where from and where the package is going to, from DS and to DS. Then we see whether it's fragmented, whether it's being broadcasted, or the access point, or rather the client has energy saving right now, so it is suspended. That would be the cell phone, high energy saving mode. It only shows the packages in and out. If it is a protected frame, which is the penultimate one, it indicates, for example, for a protected frame, it indicates that it is encrypted. So it's not an open network. That could be a web or WPA or WPA2, so it is encrypted. That means that the information transported, if it's a 1, it means it's encrypted. That is protected frame. And then the order, that is the number. The sequence, if fragmented, I'm not interested in that now. But as part of that dissection, green side, we see the body of the frame, and the frame body is interesting as well. If it's a beacon, which is a access point that keeps on transmitting, I would like to know what's the exit or the S6D or the name of the network. Here it would be CyberCamp Wi-Fi. S6D becomes an information element, and that information element, well, there's, for example, 0, which is SSD. That's the the network name, and then, well, I will only focus on 0 here. Just S6D for the network. Sorry about this, but we also realized that there was other headers. And yes, there were others you can find here, such as radio tab header, which shows information as well as SCAPI, and it embeds it all, information on very interesting things, such as what signal for the package. And that's why is it interesting to see if the access point is closer or further away from me. So based on the signal I get from the package, I see that I'm closer or further away from the network. If I want a signal finder now, I program it, and the only way to get the signal for every package from an access point or a client, it would be through the radio header. That's where I get the information. If the driver cuts out that layer, and it happens because your Wi-Fi board might be poor, you never see the signal of a package and never know whether I'm far or close to a Wi-Fi board. That shows interesting information. And so, what about this? This is the way it looks like. Wireshark shows the parsing of a package. Here you have it. This is the package as it has been dissected. We said the packages have several layers. I will use a bit of this. All right. So this is a package I have. Okay. And here we have it. There's a beacon frame. This is an access point. And that beacon frame has an frame, and initially it is frame 1. This is capture information, but if I move on to the second field, this is radio tab header. Radio tab header. It has not been filled because this package, I've built it myself. It is not real. It is not an access point. So I added a generic one, very generic, to send it up in the air. But once we capture any package, the radio tab will feed us all that information, as we said before. That could be the signal, the channel features, and where it's broadcasting from. So it is a beacon, and on layer 811 we would see type and subtype. Same as before, we can go here, same as before, and we will see type and subtype. Type and subtype. So Wireshark shows that to me as well. That would be 8. Type 0, 8 subtype. That's a beacon. That's basically beacon. And here we have a frame control. Here we have so many flags in it. Right? So we see the frame control, we use it, and we want it broken down by Wireshark. It says version 0. Not very interesting, as I said. Type 0, subtype 8. So I know it is a beacon. And what other flags are there? DS, well, and it says DS is 0. From DS and to DS, both are zeroed. And why is that? Because this frame here is not moving to the wire side, or is not coming from that wired part. So it's a beacon to the air, and it will always stay up in the air. So the DS is 0 on from and to both. More fragments I'm not interested in. Protected flag, again 0, so it's not been ciphered, it's not been encrypted. And what else do we have that it is interesting? So addresses. So source is a 3COM. Is a 3COM comms. That's a manufacturer. That's a beacon that seems to be manufactured by 3COM. So the source and the transmitter's address, because the source is a beacon that it's sending out in the air, and the transmitter is also an access point, so it's the same address. So who is this destined to? Everyone. It's a broadcast. And why is that? Because beacons are for everyone. Everyone can see there is an access point there. So if we move to every other layer, as we said back there, we have target parameters, and we said, okay, tag on exit is 0. Let's check it out, our table, and we saw here on the green side that this tag 0 equals exit. So we are dissecting it, right? We are already seeing the content and what's transported by an exit, which is empty, because it might be that, well, there are some exit points that hide the exit. They have a hidden exit. So they're here, but they don't say I'm CyberCamp, but they just say that if you know what the name is, you get connected. This is what it means. So this is for us to see how to dissect a package seen from two different approaches. Same from the side of Wireshark, and then now seen as shown to us by Scapy. Scapy has a tool which is PDF dump, which gets any package or packages and prints them just like that. And it shows the dissection of the package in a beautifully displayed way. Let me launch it for you. This is radio tab, this is the radio tab header, and here we have type, subtype, protocol ID, which is the sequence number, beacon as well. And here, on information element 0, there's an exit transport, which is owner E1F1. That's the exit transported by this beacon from an access point, which is, well, the same, this is it. So we have 4 fields and we can produce this initial tool, all right? And so the tools shown by Scapy are quite practical, but if we say print the package on screen, so this would be it instead of a PDF that you sent before, but this is the way that Scapy has for printing the package. And for this dissection of the package, so print it and show it to me. So this is the front layer. So what important information do we find here? So DVM and signal. Since I've produced it myself, it's at 0. There's no signal, but usually we will find a value here inside, such as minus decibels, minus 70 decibels, or 60, minus 60, minus 50 dBms.
Está muy cerca el punto.
So, if the access point is very close to me, if it's right next to my computer, the value might be 0. But if it's really far away, 2 buildings away from me, and I just see it from time to time, it might be minus 80, minus 90. So the closer it is to 0, the better the signal quality. Here is where we can see the dissection of the layer in Scapy. It says the type is 8L, that is type 0, close to that. And here are the addresses. Address 1FF, addresses 2 and 3 are the max for the access point because it's a beacon. The sequence number, well, we can see the layers there. It says short slot. That's not interesting. It says double S. That means it's an access point. It belongs to, or it is, a Wi-Fi network. And then it says plus privacy. That means there's encrypting, whichever type it is. So that's what the package impression is like. And here we have the information elements within the payload in the frame body. Can you see that? Those are the information elements. The information element called ID, SID, that's 0, is WL Lantre F2. Well, that's probably enough for us to start with our first Scapy program. But before we do so, I want to tell you about a script I use so that cards can work on monitor mode, because when you first plug it in, it's on manager mode to connect to a Wi-Fi network. The monitor mode is for hackers, so it doesn't come by default on that mode. You need to manually set it for monitor mode. There's the monitor SH that does that with me. I will show you that in a minute. And the SH monitor does this. Let's launch it so you can see it. Monitor SH. You first plug your Wi-Fi cards into the Wi-Fi. I have 3 cards. I have my Intel. I have a little one, which is like a toy card. I'll pull it out and show you in a second. It's very small. It looks a bit like a pen drive. And then my TP-Link. the Ateros one I mentioned earlier. So I can work with all three of them on a monitor mode at the same time. That's the beauty of what I'm showing you. All three on monitor mode, stopping the necessary services. I run that, and it says disabling the flight mode, because mobile laptops also have that these days. Then it stops any conflicting services on Linux that go against the monitor mode. That means any service that modifies anything that has to do with Wi-Fi. That's no good for hacking, right? For instance, the WPA for Wi-Fi connections or the Wi-Fi manager, a typical button that connects to the Wi-Fi network graphically, that can't be on because it will be a bother. Anything that touches the Wi-Fi card has to be disabled because I want to be in control. And then it says geographic mode changing to BO. That's Bolivia. Why? Because it's a country that allows for more transmission power than other countries. So the system will think I'm in Bolivia so that I can transmit with more power. And then it says monitor pad being created. That's physical card 3, channel 11, so that all my cards will then be located on channel 11, because I want to talk from one to another. They both should be on the same channel, otherwise communication would be impossible. I can't be making a program and have one card on two different channels. They should both be on one or channel 1, 11, 5, whatever, but both of them on the same channel. The script gets all the cards to be on the same channel. So if I press stop here, it would be quite the opposite. It would start again the Wi-Fi services, it would get rid of monitors, and it would again create normal cards so I can connect up to the internet. You see, normal cards connected. If I run it again without stop, again, I have all three monitors for the three Wi-Fi cards. Why am I doing it again? Because I like seeing this? I do, but that's not the reason. Look what it's doing now. You couldn't see that earlier because the monitors were activated, right? So the first card, Mon0, has allocated randomly Cisco as manufacturer, and two other manufacturers for the other two cards. So I have faked the MAC for all my cards. I'm a hacker, right? So I might as well do this. I can't go and attack somebody and say, hey, this is my public. If I'm going to do a pen test, whatever, I'm never going to expose my original MAC or my Wi-Fi card, because otherwise that could be traced back to me. Your MAC address can be traced. Remember that. So I changed that on all my cards. I showed you how. I get rid of WLAN 0, 2, and 14 that work not on monitor but manager mode, and I create the other three mons. So here are my three cards on monitor mode for me to use whenever. A good hacker would then check if my monitor mode card can work with injection or not. So let's check that. Will it inject Mon0? Well, ID. Which card am I testing? Mon0. Just one single step, and it's all ready. It's now saying it found 2 access points, and it's going to try and inject with packages transferred to those access points to see if there's a response. And funnily enough, Paco Pepe is on channel 11 and PRN 2 Those two guys have not replied. 30 packages have been sent and no response. So my feeling is this card is not good at injection. Let's check another one, another card, the white one. My white card, the Ateros one. You see, that would be Mon2. So I'm going to ask Mon2, and straight away it tells me, hey, injection is working. Great. Injection is working. But there's more than that. You see, injection is working successfully with good coverage. Great. That's that done. Now I can tell it to check if injection is perfect or not quite. So inject from Mon2, I'm saying now, to Mon, what was it, 3 or 1? Let's check. It's Mon3, the next one. So please inject from Mon2 to Mon3. Transmitting through one, receiving through the other. That's injecting fine, going ahead fine on channel 11, logically. All access points found on channel 11, or the ones, a long one, Movistar, Vodafone, well, a long list of them. I just want to wait and get to the end of this, because look what it does as the last step. It says, I'm going to try and inject card by card, launching different attacks. And then it says, hey, type 0 worked, type 1 worked, open with PSK, but 2, 3, 4, and 6 worked well. And what didn't work? 5 and 7. That tells me that not all cards work the same. So if you have a card with monitor mode that works with injection, please check, because they can't all inject any package. It's important then to have the right hardware depending on every situation. So this is what Monitor SH does. This is my script that I use, that I'm sharing with you today. And it can work with 2, 3, 10 cards, Wi-Fi cards. They will all work with Monitor SH. We could look at that code in more detail, but let's skip that, because I want to work now on SCAPI with programming, starting from the beginning to the end with a real example. My first program on SCAPI then. Here we have the initial lines. The first one defines and says this is a Python script. It tells me which Python version I'm using, 2.7 in my environment. And you need to use UTF coding, because that will allow me to find access points with, say, Chinese exits or exits in Arabic, because there are different types of coding. I could have a Chinese exit or one in Spanish with different alphabets. UTF-8 normally allows for different for encapsulation in different languages with different codes. So it's important for you to tell Python to use that. And this is the first line of my programming. From scapi.org, import asterisk. That means the library with all the functions and classes. Is that ideal? Well, it's not, but because this is a foundation lesson, I'm not going to confuse you and say, ooh, let's just import the functions that we are interested in those libraries. Now, that would be a bit too complex. Let's pretend we're idiots and import it all. If I, at the end of the day, I would import just part of that, but I'm now going to import all of SCAPI. Then I would create a list, an empty list that I call API list. It's a single dimension operation. I then add access point that I find on the way. I would add them to that list. For instance, I would add Mac to the list. And next time I see it, I wouldn't be parsing it again. I just parse it once. That's why I need this list. Because packages and beacons are transferred all the time, saying, hey, I'm here, maybe 10 times a second. And I don't want to see 10 times a second saying, hey, I found this. I just want to see it once. That's why I've added AP to the list. Right. Let's go to the end now. It says define a function. On Python, you use def. So def packet handler. That's what I say, and leave it at that. Because the program sequence would then start on the last line after importing the SCAPI library and starting with my IP RAI, it would start on the last function, which is the sniffing function for Python. Because Python can sniff, right? How? Through the sniffing function. It doesn't matter if it's Ethernet or 802.11 or whatever. And where? Well, on whatever interface I tell it to do. It might be Wi-Fi or Ethernet, sniffing everything that goes through Ethernet, because sniffing is a universal function and I need to define which interface it needs to do. In this case, the internal card on my laptop. And I then define a function so that every package it finds, one by one, it will be transferred to the function I tell it to use. For instance, the packet handler function being called 100 times, which is really practical when you manage packages. Hey, this is a package. Is it mine? I'll process it. If it's not mine, I'll skip it. That's the type of filter we'll be applying. A package that's found up in the air, and I need to decide if I need to filter it or not. That's the packet handler function. Here it is. Define the packet handler function. And the argument, SCAPI and sniff, that's the package. A package is an object with a number of different fields. That's what SCAPI does for us, defining the package with origin, destination, type of package, subtype, and so on. And then I can ask my object, my package, where is your destination? And it will tell me it's FFFF, whatever. So this is what we do first. This is a great initial filter. So that if the packet has layer .11, then go ahead with it. If it is not, then please discard it and continue with the next one. That's the first filter. So if the packet is subtype number 8, then that's a beacon. Well, that's a good one, right? I'm interested in that. Then I say if address number 2 on the packet, which is the origin, right? If it's not on your root list of AP, then please continue. Why is that? Because the first time round it will go through. But because I've added it to my list, then it won't the second time it finds it. Then it says, then it adds address number 2 to the AP list. So the next time round, it won't be going in. Then it says, what do you need to do? Well, I want to show on the screen that I found a packet like this. This is my first Wi-Fi scanner. and the field will be address number 2. That's the access point MAC. And then packet.info. That's the exit. That's it. So let's test it and see if it works. So we go here and we say server pay scapi test. This is Python now. We run that. And this is my first Wi-Fi scanner finding on channel 11, which is where I am. 1, 2, 3, 4, 5, 6, 7 access points so far. My first Wi-Fi scanner. In just 10 code lines, I've got my own Wi-Fi scanner. Is Python programming simple? It is, if you know your protocol, if you know what you're doing. So let's continue then with the next program. That's the title of the conference, really, my conference today. This is a program that has a client and a server. And then what I need to do, let's imagine this screen here is my server. And here on my right, I have my client. My server is my data center, and I need to communicate with it in a safe manner and with nobody knowing that I'm communicating with it. How can I do that? And how can I make my communications protocol safe? Well, I give it a script, server pay, and then my station, I give the other one. The server will just listen, sniff the traffic, the Wi-Fi card traffic, and then the client would send requests so the server can respond. That's how the infrastructure works with the client and the server. Because at the end of the day, it's a shell waiting for me to tell it what it needs to do. I say, find a beacon frames for a specific MAC. Which one? I don't care. I make the packets. So let's pretend the MAC is like a secret code that the server and the client need to comply with. So if they both use the same MAC, it's all fine, because I'm going to make up the MAC, right? I'm going to call it 01, 02, 03, 04, 05. So my MAC will allow for communication between the client and the server. So when the beacon gets to the destination, then it runs, well, the client sends a beacon to the server. Is that weird? Why do I use a beacon? I could be using anything. A beacon, just as anything else. It could be any type of frame. I decided to use a beacon. Fair enough. And then where can I insert what I want to transport, which is my command. For instance, an ls of the content of a directory. ls. That would be my payload that will be inserted into a beacon. The client will send it. The server is sniffing out for beacons with a particular MAC. Everything else is going to discard, right? So once the payload, the contents of that beacon, the ls is extracted, then that command's exit will go to the client within a prompt request. Why? Well, just because. I just like prompt requests, but it could be any other frame. This is how it works. It goes to that particular MAC. That's the target. And this is a proof of concept. It's not a commercial tool, right? It's just a POC. So the maximum size of the MTU has to be a reasonable size because it wouldn't fit on a prompt request. The maximum size is the size of the package. It has to be encapsulated within different fields in the packet so it can get to the other end. And then what would the client do? The client has a shell. I will show you right now. It reads the user entry. For instance, if I say ls, so that's what Python reads, ls. What does it do with the ls? Well, it encapsulates it within a beacon. It sends it to a Mac, particular Mac, as a beacon, and then it stands and sniffs the exit of the command it's running. When it gets the frame, it's extracted as 5 different information elements. We will see that in the package. And why is it 5? Because the maximum size for an information element is 256 bytes. I need to cut it into different fragments. I can't have it whole. And encoded on 64 base, because that's practical. It could be binary, but anyhow, that's what we'll do. Here we can see an example of how the building of the server works. Because what the server does is encapsulating the commands. In what fields? Here in the information elements. There you have it, 0, 1, 2, 3, 4. That says base 64 first part, base 64 second part, and so on, so that it can be encapsulated and cut into different fragments, which are 256 bytes each. And that's what the package contains. That's it. So what would the client do? You ask it for an ls, and where would that be included? Here, an information element. And why is it ls? Just because. It could have been anything else. From 256, it could have been any number. If I have a monitor mode card which works fine, I don't care if it doesn't comply with the standards, right? Let's have a look. Let's run a demo and see how it works. Right, my cards, my good cards are Mon 2 and more, Mon 3. The 0 one didn't work. Mon 2, MON2. So I'm going to run the server now on Mon 3. Sniffing. The server is down below at the bottom, you can see on the screen. And what does the server do? Well, sniffing traffic for the packet. And what is happening at the top, up above? Well, I have my shell there. And if it works okay, I will do ls, and then down below I will see how it's receiving SLS. It encapsulates that response and then transmits it to the client. Here I say with another command ls, well, at the top, and then down below it would show. It's the same thing, client, server. And I can do this with different commands, well, depending on the size as well. I could transmit different prompt requests and beacons, so I could have a very large packet if I was manufacturing, producing something, but I'm not. This is a proof of concept. If I do a very large ls, for instance, user bin. And there's a D at the end. That's the most it can give me. Why? Because it's a proof of concept. so it's limited. So, for you to see more information, let's now exit the program. So I can make the program look like a bug. I have a number of verbose modes, you see, 1, 2, and 3. And here we can see the MAC they both use for communications, as long as the client and the server use the same one for communication purposes. Let's go for verbosity 1 for the client, and the same thing for the server. Here, verbosity, well, the same MAC, right? You can see that down below. Verbosity 1 again. And let's see what they both show us. This one is sniffing, and this one is transmitting. Let me just refresh the screen so that you can see it better up above. Here I do ls. I run an ls. And because I don't know if all the packets will get to their destination, I'm going to send 10, because some might be discarded. Down below, what can I see? Well, I get more information there. It says, oh, it's requesting for an ls. The command exit are 123 bytes, and on base 64 encoding, here I'm going to chop it into these fragments, which are 232 maximum size. If I raise verbosity to level 2, we will see a little bit more information.
So this is you as well. I run the client up there, the order doesn't matter. Down below, I run this. I'll try to run another ls. LSA does not exist, so this is a wrong command. It does not exist. But so LSA, this is a command, is not existent, but it's built another package which has first radio tab, which is a dummy. Okay, it's a dummy, it's a lame, it has no real element. I'm not interested. But I'm interested in 811. That would go into a beacon, which is a subtype 8 and 0. So here you have it. LS2, that's the destination, is 1, 2, 3, 4. That's the DS, and that's the communication channel we've built for it. And we see that LS or LSA here, it's encapsulated into an information element, which is rates number 3. And this is basis 64 for LSA. This is what we're saying. Same down here. And I increase verbosity a bit more. Down to 3. So this is here, and this is the server. Bit bigger. Another LS again. This is what we had built. But let's try and see this, the exit here. What you have here, what you see here, that's the exit that is base 64 encoding. That's the full one. That's the result of the LS. This is what you can see here. What you see here that I'm highlighting, that's it. But encoded on, it's a base 64 encoding. If I run a base 64 decode, I show what you see there. And then you see down there, first information element, I've encapsulated it, full encapsulated it, right? So that's the first information element that I have fed it in, but nothing else, not for any other, because the exit here, the size of the exit does not need nothing but a field, because it's under 152. So the first information element encapsulated it all, but I can use up to 5 here. So you get an idea, basically get an idea of what I'm doing. Inside this sequence. Let's see the code because we have some time left and we can play around with the code of both programs. And let's try and see what the simplest one does, the client. So same thing here, first line. Import the libraries I need. Python. What libraries do I need? So I need the system library login. Why is that? Why is it using it? Because I like to log it all. I like logging it all. I like to have a log of everything I do in my life. So I don't have a video log. I don't know why, but I do like logging every server. So when I say to the server, run this command, it is logging it all. I've been asked to record it, log it, this time, this hour, and it's all on syslog. That's the way to work. So the base64 library, you've seen I've used it, and readline to read line by line the command exit line, and then I import the Scapy library you saw from Scapy all import. Previous one is so that we don't have this typical mistake bug on Scapy, but that's all. And there you see how we have verbosity, T, Mac key, what I'll be using as communication channel between both server and channel, and ZMD, which is an empty variable that I will publicly use to populate the command exit. The interface goes on command line. I run it on mode 0 or 2, and same with interface. If I don't have the interface, there is a warning. The script needs to be used like this, so it gets out of the implementation. Then I do something very beautiful. That is, I use a history. All of us programming on Linux, we love it. Arrow up and down, and we see the history of commands. This is something snap of myself. And then you have the packet handler there. This is what we saw was the packet handler, as defined in English. So let's run to the implementation, which says as long as CMD variable does not equal exit, it stays in the loop. It stays in the loop. And what does the loop say? Print shell with an enter first. So you go back with a return. Beautiful, as you've seen in the screen just a minute ago. And it gets the input. So it's a raw input. If I enter ls, the CMD variable is populated and is defined, which is ls. So CMD will have the ls value. So I say, okay, if CMD is not or does not equal exit and is now empty, then use readline library and have the history, as I said before, arrow up and down to save the library, but doesn't matter to you. Still, here I have not typed exit, so I'm not coming out, but run the command that I'm asking you for, that's ls. It says go same frame function, so use base64 encoding for the ls. That's what you will have in the packet. All right, so you will see that, and this is how you build it on Scapy. That's a way to build a frame. A frame is nothing but an object. A packet is an object when we talked about Scapy. So it's all layers, layer plus layer. First layer on an AOT11 is a radio tab, which is a dummy. It's a dummy because I will not be adding any other element, but as it's built, we would need a radio tab at the beginning, and it is fed empty, and that's it. This is layer chaining. / equal means chaining. And I chain the following one. That is the 211, 802.11. It has a series of fields in it. Address 1, 2, 3, 4. So a series of things that we have on packet 802.11. So we say address 1 is broadcast because it's a beacon. This is for everyone. And address 2, that's a MAC key, which is a variable I define 01, 02, 03. That's a communication channel. This is what has to be embedded into the packet. And then I have a random MAC address that can be changed with every delivery or every transfer. And what else on the package? Well, I will add another layer, which is the beacon layer, which is a beacon, and so it has to have a beacon layer on top of everything. So what capabilities are there? Well, this is an access point, so it's an SS. That's all. It is standard, no trick to it. And what else? Information elements, that's where I will embed my information. So information elements, what information elements will you be adding? Exit, which is 0 is exit. And what would you add? Nothing. Nothing. I just leave it empty. I'm not interested. Exit is empty. The ls command will be embedded into information element 3, that is range. I could say id equal 3 because it's id equal rate. And then payload goes into there. And what's payload? It is the variable that I get with the base 64 and ls. And what else? I don't really need to add anything else. From here onwards, I say, send me this frame 10 times over. All right, I'm sending this 10 times up in the air. I've built it and sent it up in the air 10 times. I broadcast it 10 times. Then sniff for answers. So you've sent the request. Now try and listen to the answers. So you sniff the server traffic that is destined to you. What's the function, the feature? Sniff feature, the only one that Scapy has for sniffing. From what interface? Well, the one that you send me through the prompt, mon 0, mon 1, whatever that is. And what we'll be using for a packet passing then? Packet handler. So we go to the packet handler's feature or function. So it sends me the package, any package coming in from the server. It is sniffed. So what filters do we have? Easy. If it's .11 or 802.11, it's Wi-Fi. Yes, it is. Good. If it's 0, management. And subtype is 4, then it's prompt request. And if address 2 equals our MAC address, then I process it. If not, rule timed. But if it is, process it. And so here we define information elements in the packet with just one variable or object. And so we say ELT, take it out of the information elements of the package object. So I have another object here. This is only information elements, and I'll process that. And so I say, as long as you're reading inside of that element, any element that is an information element type, process it. And so we say, okay, if it is 0 as an information element, then the exit is what you had plus this value. If it is 1, so what you had plus this field's value. And so all the way up to 7. I'm using 5 here, right? You've seen that. But for 7, it all cracks because it's too big a packet. So I decided to go to 5. So what do? I chain together. So information element 0, 1, 2, 3, 4, 5. So now I have a base 64 and also the command exit ran here. So that's it. In the very end, I say print it on screen. Base 64 decode for the chaining of the fields. All right. And so if it replies true, then back to work. Right here, you can stop sniffing because the answer to your question has been given. Then again, another prompt or another command is prompted. Basically, that's the way to encapsulate. If we see that the code from the server, well, it is just the same, and I'll show it to you so that you see, but it's just the same. Basically, only thing that matters here is while true, so listening to the package, and you show a message on the screen, sniffing package. Okay, perfect. And from here you keep sniffing using SCAPE. What interface they want to given to you, and what's the handler for the package? Well, the packet function. If there is an exception, throw it to me and get out. So our packet handler, that's what matters the most. What's most important. And here we have it. This is, well, packets I said, right? Here it is. This is what it does, is it just sniffs. If it's 802.11, it's Wi-Fi. So move on. If it's 0 and subtype 8 of a beacon, what I hope I can hear from my client, that's what they're saying. But then address you in the package belongs to our MAC, so the communication channel, I will process it. And it says CMD, which is the command that you requested, which is an LS, well-known LS, is a string that has a base 64 code for information element 2. Okay? So that's what's inside that element. Okay, then, out of that information element, it's not 2, but it's 3 rather, but it is 0, 1, 2. So you get the CMD, which is the ls command. You decode it with the base 64, and you run it with that function there, with that feature there. So execute here, that's the name. And execute here, there you run ls, and you said, this is the ls command that you requested. I log it because I say I always log it all. And so I say that's the command. And so you open a sub-process in order to run it. So you need to open it. I will not do it on the main thread that is always sniffing. So I open a sub-process where you open ls and the exit, which is spd out, and also back exit comes from process communication. You remove the /n, which are the changes in line, and you see whether it equals 0 or, well, this typical things. It's a well-programmed script. It will not just crash with anything. It will not just crash with anything. This is a typical filtering or cleaning out. This is the exit. Okay, so I forget about all that, and the exit is out. That's on screen. That's an ls, and I have a command list. So base 64 encode, because that's how it's been encoded, and it's out perfect. And then just you split it into pieces, and it 5 pieces that are to 152. That's the size. In one just information element, I cannot fit 1024. The biggest size is 255. That's the top threshold. I limit myself to 252. That's what's normal. I encode it into pieces. Great. And from here onwards, I build the packet that I'll send. Same as before, rated tab, and then type 0, subtype 4. That's where I'll be transmitting. Broadcast direction or address. Address number 2 is the one that will be sniffing. That's the MAC address. Address 3 I'm not interested in is a broadcast, and here we have that inside of all 5 information elements 0, 1, 2, 3, and 4. That's where I placed 3 pieces that are 2 and 52. That's what I cut out of the exit. So what I do next is I send it. Well, many more things actually, because actually what I do for it to be instructive, I use different levels of verbosity so that you see what it looks like, what I'm broadcasting. So here you can see that one of the things I do to see the power with a prompt, just one prompt, one command line on Scapy. I'm logging it on a PCAP full file. So that's what I'm doing. I get this rec file and I'm putting it into a rec.pk. And with that, I just send it. So this is the send p function that we use for .11 because that's a layer 2. If you're sending TCP, IP, you would use send without the P after that. But if it's layer 2, you use send P and then you state which interface. Or so first, what do you want to send? This would be just one packet, one frame. This is what I built up here. This, you send it to me, and which interface? Moon, 1, 2, whatever I've chosen. Verbosity level, not very much interested, but how many times over? 10 times? Well, same as usual. If there's an exception, you try and send the exception as well that you've produced on the server side. If there's an exception running, because you ask for a command that is pointless or that's produced a mistake, I send the exception together with the to the client side, same way. A request with the radio tab and the content would be the exception. All right, that's all. Actually, if you think it through and you get yourselves familiar with the protocol, what you need to do is know the structure of the package. Now that we know the structure, if we know what every field is or what our fields of interest are, with the Scapy you can do it all of it. So, that's, in a nutshell, what we can do with the Scapy. This is just a proof of concept. Whether useful or useless, I don't know. But the idea would be to open up your mind so that you understand what we can do with network hacking. Is not just using third-party tools, but we can also use tools that we've made ourselves, and that's all. If there are questions, we have 5 minutes left, if I'm not mistaken, for questions. So any question you might have, now is the time and the place. I think there's a microphone out there, isn't there?
Sí, oye, una preguntilla.
Dime.
Todo el código, todo el código que nos han mostrado está...
Aquí.
All the code you showed to us, yes. There you have it. Take a picture if you wish. This is my GitHub, where I have so many examples. You get the examples from the book as well. For this GitHub, there are some Python pieces of software that help you learn Scapy and some other things. So thank you very much.
Aquí, delante.
Sí, Iago, mi pregunta es...
Simple question and quick question. CRC in the packet. Well, Scapy does calculate the CRC. FCS for 802.11. So it is preset. The calculation is preset. Actually, as I was defining parts of the packets on Scapy, I would have the source and destination address type and subtype for 802.11. But there we have many more things. All those things that are not defined on the Scapy is because they are pre-set or default. If I don't fill them, they fill themselves. Maybe not with what I want, But so it's easier that the packet is a full packet. If we want to go deeper, we can play around with others. Sequence counter and others, they're all accessible as long as you know how to build them. Because sequence counter, the number of packets or sequences, I'd say is a sequential number, usually. If it starts with a 1, 2, 3, 4, it will stay sequential, but the full byte or 2 full bytes are not used, only part of one byte and part of the other. So in order to build it, we need to know how to build it. Cannot say sequence counter is 1 and this will be admitted, because the top is 4,000 plus. And if I say it's 8,000 plus, something weird will go on. And it will fill parts of other bits in the packet with that sequence counter. So we need to know what we're doing. And if we don't know what we're doing, give a chance to Scapy to fill it for us. That's the idea. Thank you very much. Any more questions? Hello, Iago. I have a question. Thinking a bit, well, with a bad intent. Well, no. I can take revenge next time. So if I were to simulate a access point with a Scapy with the same SSID and the same MAC address as with a hotspot for my cell phone, would the cell phone try to gain access to that? Yes. And maybe with a grab attack or something similar, we could get the password out of the hotspot, right? Well, the password itself, no. It depends whether it's WPA or what we're talking about, but if we focus on thinking that, well, web is not available anymore, and we think of WPA, if there is a attack is similar, I start sending beacons with Scapy, as we've seen, it's easy, it makes sense, and so I start sending beacons, the right beacons, properly structured, and then a series of beacons per minute or second, let's say 10 per second. So I start scanning with my cell phone and I'll see there is an access point here. Okay, that's true. But then you've only done part of the attack. Then on Scapy, you just is sending beacons, but it's a dummy. Then you have a virtual access point which is not existent, does not respond to packets or probes. If you want to have a slightly functional access point for an attack, first you need to send beacons and then reply to prompt requests with prompt responses. There you would have on one hand, you can send beacons, then you can sniff, and then sniff and see if there is any prompt request to you. If there is, then you reply with a prompt response, and there's where we got more implementations. An access point is 1,000 things. Authentication request. I'll let you authenticate yourselves and I give you a response that's open. There's no authentication yet. Even if the name is authentication, there's no true authentication there. Then we have the association request or response. It will send an association request and you will send an association response. Up to there, you're complying with what 802.11 says, but then WPA. And they say, well, the key and everything else, that's different. It's not the same protocol. Scapy does have support for that other protocol, and there you can build EAPOL protocols and encapsulate them right. So there are several tools where there's one on Python where you actually first step is you send a challenge, right? Through it, and you send an announce, which is the access point. It sends a challenge and the client, the station that is, encrypts it. And there's the second part of the authentication on EAP, that is the S node. So the access point is authenticated by the station. It is a double sensor, the two-way rather, that's the name, two-way. So using the EAP and you send a number, random number, which is a challenge, and there's a reply with the nonce encrypted, and just with that you can send it to Hashcat or aircrack NG for it to decrypt it, or send a dictionary to decrypt it with brute forcing. And there's one here, one there. Then we use this as a means of protection. For example, if there is a man-in-the-middle attack, to send a forged, a fake frame. So there's another password. And so we can also have a honeypot on there. Well, Scapy, for 802.11, that attack would be complicated, because if two devices, both devices, client and the other device, are unaware of the key, they cannot talk to each other. That would be basic. That's the Wi-Fi. So both need to be aware of the key. If one of them is not, they cannot talk to each other. Same if Japanese and Chinese, well, you speak Japanese and Chinese, even if they and I speak Chinese, even if they look similar, we will not understand each other. But if it changes to more protocols, it's an offensive and defensive tool, both. In my book, one of the scripts defined is a personal IDS, where you and we saw, well, there is this Wi-Fi board, small one, that is stuck to one side, and this is minimum, and this is a monitor. And with the script on the book, which is a personal IDS, you detect the authentications against me, and then it protects me against networks I do not trust. So it's constantly on Linux, right? But it is constantly scanning, trying to see whether I'm being de-authenticated, whether I'm being kicked out of a network and into another. So we get constant information on screen. You say you are trying to be kicked, someone's trying to kick you out. Maybe you're going into an untrusted network. And so in offense and defense, you can program it on Scapy. So it's very useful. Thank you very much.
Una pregunta creo que es fácil. Una Mac.
An easy question. Can a Mac have several SSID? Yes, of course.
A día de hoy.
Right now, physically, the limitation is more or less at 32. An access point, which is good quality, can go up to 32. That doesn't really matter. The same channel, really, the limitation on a channel means that it has a radio, and that means that it can only have one channel. But an access point can have up to 32, as many as we like, with different types of security levels. One open, another one web, another one guest, another one for client. They can be on different WLANs. And on Scapy, we can also design a simple attack with overflow on Scapy, transferring beacons from an F point, for instance. And you will find in my book a script where you take it home, scan, and then record it on a PK file. You then go to your office and run all the networks you found at home and clone all those features. And when I say cloning, it's not a fake AP with Airbase and or Karma, those tools that run a false one. It would be an exact clone with the exact same features, and that can be done with Scapy quite easily by capturing a beacon and a prompt response for a real access point, and then you broadcast that up in the air, and then it looks like a real one. Some attacks can run up to 50 access points like that. And if you scan Wi-Fi networks like that, it really overflows. And that can even make the Windows stack fail. But you can do it, yeah. Any further questions? Great. Well, thank you very much for coming and attending my workshop. And see you next time.